CLion, a cross-platform IDE for C and C++. Download now.
Hello, everyone. Thank you very much for coming. My name is Ofek, and in the near hour or so, we'll discuss concurrency and memory models down to the hardware level. So first, let us go over a toy concurrent program in pseudo-assembly that can demonstrate a few interesting phenomena. One, writer core writes the value new into a memory address called data, that is the variable data. After that, it writes the value true into a variable called ready. In parallel, a reader core loads ready into the register reg1, then checks its value, and if it's false, returns to loading ready. When the reader core exits this loop, that is when it read a ready value of true, it loads data into a different register, reg2. This does look like a well-formed program. Our normal intuition tells us that every instruction happens in some single point in time. It may be before or after other instructions in a different core, or after but there is some single timeline on which all cores can agree. This natural intuition is captured in the notion of sequential consistency. It is the simplest memory model. We didn't say yet what a memory model even is, but we will soon. Sequential consistency doesn't say what is the exact interleaving order of instructions. It just asserts that one exists and that all cores agree on it. In this example, the writer core finishes before the reader core even started, but the program does work as intended. In this example, the reader core started first. The reader core started first and loops a bit until the writer marked ready as true, but the program works either way. I think, but not entirely sure, that in the first few generations of multi-core processors, this was actually how hardware worked. But these simple days are long gone. We will step gradually into the complexities of modern systems. For that, we will need to zoom into memory reads and mostly memory writes. Modern multi-core systems have a hierarchy of caches. L1 is pretty much always private to a single core. L2 is sometimes private and sometimes shared among a few cores, and L3 is pretty much always shared. But for the first part of the talk, we will neglect all that. We will neglect the memory hierarchy entirely and just think of the memory as a single blob that all cores can access directly. And after this preparation, we're ready to look into some hardware optimizations that can mess with the program order and with your mind in general. Here's one: FIFO write buffers. Writing to memory was found to be a bottleneck pretty much immediately when multi-core systems appeared. Because we will see in more details, but the core had to stall until caches synced among themselves and with memory. So an early attractive optimization was to buffer these writes, to make them asynchronous. And the write buffer was born. Today, processors trigger a write request to the write buffer, not directly to the cache, and get on with the work. The fun starts when the writing core and other cores try to access a value while it is in the write buffer. When the writing core tries to read the data, it is able to access its own write buffer instead of the cache. This is called a bypass, and gets the value new. A different core, well, all it can do is access the cache memory system, and there it sees the previous value of old. So here, for the first time, we can see points in time in which different cores do not agree on the values in the same memory address. They have different views of memory. And so it is time to start talking about memory models. A memory model of a system is what can the system guarantee about all views of memory, even if they are not identical. Now that different cores don't have the same views of memory, the answer would eventually turn somewhat complex, but not yet. It also needs to be said that this usage of the term memory model is the typical one in system design. When C++ standards speaks of memory model, it typically speaks of how many bits in a byte and constraints like that. I will try to make the distinction where it is meaningful. So let's try to understand what can be guaranteed here. Observe two writes, first data and then ready, and let us pause when the writes are in flight in the write buffer. Currently, the cores don't agree on both values. The left core sees data as new and ready as true, and the right core sees data as old and ready as false. A bit later, the right core thinks the data is new, but ready is still false. And eventually, the right core thinks that data is new and ready is true. At this point, both cores agree. Our toy program does work because both cores agree on the order of the two writes. This memory model is called TSO, Total Store Order. All cores agree on the order of stores initiated by a single core. And this, in fact, is the model exposed by that is guaranteed by x86-64 systems. In reality, if you're writing such a simple reader-writer queue, where you intended to run just on x86-64 servers, you really don't need to add any atomics or locks or any synchronization whatsoever to make it work. Right, let's take another step. Modern architectures like ARM and RISC-V typically have write buffers that are not FIFO, but rather coalescing. Let's unpack that. We said that writing to cache is kind of slow, well, at this resolution. Now let's zoom in one step further. Caches do not operate in the granularity of individual bytes, but rather in granularity of cache lines, typically 64 bytes. Writing less than 64 bytes to cache involves fetching from memory a complete cache line, or at least making sure it is already available in the cache, then making sure private caches of other processors invalidate the contents of this address if they already store it. And only after this dance, actually writing to the part of the cache line that you intended to. So this is rather complicated and dense, and it presents another attractive optimization. If the write buffer contains two writes to the same cache line, coalesce them. Do them together. Do the write to cache choreography once instead of twice. Here's what it looks like. Say the writer core writes 1 to A, B, and C in the same order. Now say that A and B are in the same cache line. A coalescing write buffer would join them into one. More fun starts if A and C are in the same cache line. The coalescing write buffer coalesces them. Now, after the coalesced write got to memory, a different core sees the writes to A and C, but not B. So here, the two cores don't even agree on the order of the writes. Let's quickly go through this again with different names for the variables. Say we write to some dummy, then to data, and then to ready. And say that ready and dummy are on the same cache line. Now, the write to ready could be coalesced with the write to dummy. So a reader call at a certain point in time can have the view of memory that says ready contains true, but data still contains old. This is not theoretical. This is the case in ARM and RISC-V systems today. If we do want proper thread sync, something needs to be added. Spoiler, fences. But before discussing that, we'll mention some other hardware sources for mayhem. Invalidate queues. Recall this slide from earlier. We mentioned in passing that different private caches can hold copies of the same memory, and that when a core wants to write to a private cache, first the other private caches need to be notified that their copy is being invalidated. Turns out that when many cores perform writes, this invalidation becomes another bottleneck, and hardware architects want to have it buffered too, to have an L1 cache launch an invalidation request and get on with its life. So, invalidate queues were born. Private cache can broadcast, well, not always, but somehow communicate to other caches that a particular cache line is now invalid, but continues to write to it before receiving an ACK, an acknowledgement that invalidations were performed. While such an invalidation message is in the invalidation queue, different cores will see different contents of memory. The writing core will see the new data, but the other core didn't yet receive the indication that the value in its private cache is invalid, and it doesn't know yet it needs to get it from elsewhere, and it does read the old data. So that's another hardware reason for two cores to have different views of memory. Now let's talk about multi-copy atomicity and about cache forwarding. So while writing a value to a private cache, it sends invalidation requests to other private caches holding a copy of the same memory. Now note that while writing is still ambiguous. There can be many other caches, many other cores with other private caches with different invalidation queues under different loads, and certainly not all cores invalidate the cache line simultaneously. So even after the write buffer spilled its contents to the center cache, discrepancies can arise. The private cache on the left got and acknowledged the invalidate, and if it needs to read the variable data, it knows to request it from the center cache. At the same time, the write cache didn't get the invalidate message yet, and as far as it is concerned, it is allowed to use the old value, still in its private cache. And all this happens after the write buffer spilled its contents to the central private cache. Now, this discussion implicitly introduced a cache forwarding mechanism. We said earlier that, we implied earlier that in case of a cache miss, a request is serviced from some shared cache or some memory, but that was a lie. When possible, such a request is serviced from a neighbor private cache holding the same cache line. And so, hardware designers introduced multi-copy atomicity. The copies in question are copies of the same cache line in different private caches. When several caches hold copies to the same cache line, if a core writes to its private cache, it will see this write before other cores because of write buffers. But multi-copy atomicity requires that once a write is visible to one other core, it is visible to all other cores. To enforce this, there has to be some central actor that synchronizes invalidate requests and make them take effect at the same cycle. The identity of this actor actually varies. It can be a cache controller or a component called a directory manager, but it is not important. Such an actor must exist to enforce multi-copy atomicity. IBM Power processor was non-multi-copy atomic. ARM v7 is also non-multi-copy atomic. In general, the ARM philosophy was to assume zero synchronization is required until the code explicitly says otherwise. But apparently, this particular relaxation became too complex to reason about, and in ARM v8 they backtracked a bit, and now they require systems to be multi-copy atomic. Even that is not entirely accurate. The ARM v8 spec does not require it explicitly, but in practice, ARM v8 system implementers do stick to multi-copy atomicity. Okay. Let's discuss out-of-order execution. Ignore all previous talks of buffers and optimization. Assume there's a single memory timeline and a writer core that writes new to data and later true to ready. Now look at the reader core. Program order is first read ready to reg 1, then read data to reg 2. The processor is able to perform some pretty sophisticated analysis of instructions dependency. And if it sees that nothing earlier in the program depends on reg 2, it is allowed to initiate the fetch of data from memory earlier. The processor does have what's called a reorder buffer, you sometimes see ROB, that makes sure instructions are retired at the program order. That is to say, the visible state of reg 2 would be changed to the loaded data only later as the program order dictates. But the actual fetching of memory can be initiated earlier, and it caught the value old. This example, in fact, can't happen on x86-64 processor. Beyond being TSO, beyond being total store ordered, loads cannot be reordered among themselves, but it can happen on ARM. And by the way, this is something that not only processors do, but compilers can do too. Compilers can change the actual program order from under your feet, pulling loads earlier if they see no reason not to. Speculation is somewhat akin to reordering, but not quite identical. When a processor reaches a branch, strictly speaking, it needs to evaluate the condition and decide which instructions to execute next. This typically involves fetching memory and so waiting, and processors hate waiting more than anything in the world, so they do speculative execution. They take a semi-educated guess of the condition value and fetch and execute the instructions based on that guess without retiring them, without exposing them externally. When the condition is eventually evaluated, if the guess was correct, the processor retires the instruction that were executed speculatively. That is, it makes the results visible to registers and caches in memory. If the guess proved wrong, the processor flushes the speculated results out, stalls the pipeline, and starts over. Now, if you're an ARM processor or some other relaxed one, you pretend you're the only thing running code in the world until someone restricts you. By default, you assume no one besides you can change memory. So when you, the ARM processor, execute this code, here's one thing that can happen. You get to if ready and initiate a load of ready from memory, but you're unlucky and it's a cache miss, so it takes time. So you just guess it's true and execute the then clause. That includes a load of data, and at this time you're lucky and it's an L1 cache hit, and you see it's old immediately. By the time the slow read of ready is satisfied, another core changed ready to true. You decide that your speculative guess was correct, and you merrily retire all the speculative executions you were waiting on, including the load of the data value old, which can be kind of annoying. Some processors do validation before retire, but relaxed architectures like ARM that operate under the assumption that I'm the only one running code in the world until told otherwise, don't do this validation. Okay, enough problems. Let's discuss some solutions. Let's start with the heavy artillery. mFence on Intel and DSB in ARM are data store barriers. Naturally, there are some subtle semantic differences, but these two are rather similar in operation. They stall, that is, they block until the store buffer on the executing processor is drained, and the stores in flight are settled in and visible everywhere. That is, all invalidate requests from the private cache are fulfilled. It prevents reordering across the fence and speculative execution across the fence. And this it essentially tells the processor, stop the world until everything before me is done. This is the safest and, of course, most expensive tool available to you. ARM provides a more refined tool, DMB, Data Memory Barrier. This flavor is system-wide, and this enforces ordering, not completion, meaning this guarantees that all memory accesses before the DMB are made observable before any memory access after the DMB. So earlier memory operations may still be in the right buffer or a right combining buffer or invalidate queues or wherever when the fence instruction is retired, but they cannot become visible externally after later memory operations. This is the cheaper alternative with mostly compatible semantics. But there are still more specialized tools. In Intel architectures, there's sFence, which is a fence similar to mFence that affects only stores. Again, this controls completion. It tells the processor to complete, to retire all earlier store operations and only then move to the instructions beyond the fence. And recall that on Intel, stores are already ordered, so it is not entirely obvious why such a fence might be useful. And indeed, for the most part, it isn't. You'd very rarely see sFences in x64 assembly. They have impact on stores to memory mapped I/O and something called non-temporal stores or streaming stores, which bypass the cache. When you see move NT instructions in assembly, the NT stands for non-temporal. Intel also has a flavor of the fence that controls completion and is applicable only to loads. I won't have time to go into details about register and naming and what it even means to make a load visible. And again, for Intel, this might look like a pessimization that achieves nothing, as Intel does not reorder loads anyway. But in fact, you do actually see L-fences in the wild, because in recent processors, L-fence is also acting as a speculation barrier. It prohibits the processor from executing instructions speculatively past the fence. This is part of the mitigations introduced against the Spectre class of vulnerabilities, and I won't go into further details here. Now let us look at some ARM facilities: load acquire and store release. These are again ordering-only facilities, as is typical for ARM, and say nothing about completion. DMB-LD is a favor of the data memory barrier that ensures no later memory op, either load or store, can be made visible before an earlier load. DMB-ST ensures that all earlier memory ops, either load or store, will be made globally visible before a later store. The names were confusing to me initially. I thought DMB-LD is the ARM analog to L-fence, and DMB-ST is the ARM analog to S-fence, but they are certainly not. As you can see, both fences impact somehow both loads and stores. What's important to note is that unlike x86-64, these fences again say nothing about completion. They do not stall the ARM pipeline. Earlier, when these fences are retired, earlier loads and stores might still be in flight somewhere in a write buffer, in invalidation queue, or other coherence requests, but they are guaranteed to not become globally visible before later accesses. These are actually, they might seem convoluted, but these are actually the most important fences because they map very closely to the C++ memory orders, as we shall see. What you will most likely see when you inspect disassembly for ARM code with atomics are these two instructions: LDAR, load acquire, and STLR, store release. Load acquire is a combination into a single instruction of a load, an actual load, and DMB-LD fence, meaning this is a load, and moreover, later memory operations are forbidden from becoming visible before it. The name comes from acquiring a lock. When a thread, acquires a lock, it must not read protected data before the lock is obtained. STLR, aka store release, is the mirror image. It is a store combined with a DMB-ST fence. Earlier memory ops are prohibited from becoming visible only after it. And the name comes from the semantics of releasing a lock. When a thread releases a lock, all work done inside the critical section must be made visible before the lock is released. And as usual for ARM, these instructions perform the absolute minimum work needed. STLR, for example, does not say that prior memory ops are completed before it. Maybe they became visible, maybe not, but when they eventually do, it would be before this store is made visible. So now we have what we need to fix our toy reader-writer program to run successfully on ARM, at least at the assembly level. The writer core can't do a regular write to ready. It needs to do a store release, right? to ensure the prior write to data is made visible before the write to ready is. The reader core can't do a regular read of ready. It needs to do a load acquire read to ensure that the later load of data cannot be reordered to before the load of ready. And this is what it would look like in C++ code. Ready needs to be made an atomic variable. The write to it needs to use atomic store with a memory order release argument. The reader core needs to read ready with an atomic load with memory order acquire. Now let's dedicate a slide to STD memory order enumeration. The effort to abstract memory order operations across different processor architectures did not start with C++. It actually started with Java, with at least Java, maybe before that. C++ first entered this minefield in C++ 11 and adopted very similar abstractions. And decades later, Rust came and adopted abstractions virtually identical to C++. So as we saw, release operations are applicable to atomic stores. Earlier memory ops cannot become visible after it. And we saw acquire memory order optionally applied to atomic loads. Later memory operations cannot become visible before it. The C++ standard does include spec for another load modifier called consume, but it is officially regarded as broken and unimplementable as specified, and all compilers today treat it the same as acquire. We will soon discuss an additional class of atomic operations, not just read or write, but read, modify, write, with two additional optional memory order modifiers. Relaxed, this is the weakest memory order. It imposes no restrictions on memory order whatsoever, just atomicity. And acquire release. That's an RMW, a read, modify, write marked with this is both acquire and release, meaning this is a full memory fence. Memory ops before this cannot cannot be made visible afterwards, and memory operations that are later cannot be made visible earlier. And finally, there's sequential consistency. It is a valid argument. It is accepted on all atomic operations, stores, loads, and read, modify, write. And theoretically, it is the strongest guarantee. Now, the range of behaviors it permits is actually narrower, the way it is specified, but in practice, I couldn't find an example for code that compiles to a different result from acquire release. Please do tell me if you know of such an example. I suspect it's currently a placeholder for hypothetical future architectures. I couldn't find a practical reason to reach for it today. So, as promised, let's discuss some read-write operations down to the hardware level. Here too, the hardware implementations of Intel and ARM diverge wildly, and C++ tries to expose a common abstraction, and there is an interesting discussion to be had here. So, the base operations that can be made atomic without locks are arithmetic and logic operators. They can be written as operators or in a functional form. When they're written in operator form, they implicitly impose sequential consistency ordering, and when they are written in a functional form, they can accept an argument with the desired memory order. Atomic exchange and atomic compare exchange in weak and strong flavors. We'll actually discuss these particular two in some detail and discuss the distinction between them. When you look at Intel assembly for atomic ops, you typically see a lock prefix, like lock add and lock exchange. And when you look at assembly, you typically, but not always, see pairs of special load store instructions that we'll discuss. And in newer ARM versions, you see some instructions dedicated to specific atomic operations. So let's start by looking at the Intel way of doing read, modify, write. In the ancient times, multi-core systems actually connected the caches of different cores with a bus. Invalidate requests and cache forwarding and whatever did travel on this bus. And instructions with lock prefix actually locked this bus for the entire system, for all memory operations and all addresses. This is, of course, very expensive and entirely unscalable. So today, the lock prefix means some very different things. So suppose a core wants to do an atomic read, modify, write on memory in some cache line. The first thing it would do is to request invalidation of any cache lines containing this memory in other caches. Then it would read this memory to a register, do some computation on it, and write it back. But being properly atomic means handling potential interruptions. What happens when another core wants to write to this memory? What happens is that in order to complete a write, the other core issues an invalidate request to this cache line. And if our core is in the middle of an atomic operation, that request is blocked until the operation completes. This blocking is per cache line. Other memory operations on other addresses continue uninterrupted. And this is obviously better than locking an entire bus, but this is still blocking. Now let's talk about how ARM does it. ARM uses a pair of instructions, load exclusive and store exclusive. An ARM core starts an atomic read, modify, write operation with a load exclusive register, or LDXR. This performs a load from cache to a register, but also it marks this cache line as exclusive to the core. In this illustration, this mark is adjacent to the cache line. In reality, it isn't. It is in a component called exclusive monitor, typically part of the cache controller. Following that, the core performs some calculation on the loaded value, increment or swap or whatever, and then a store exclusive register, STXR, is executed. This is a store that performs a preliminary check on the exclusive monitor and fails if the destination is not exclusive. So what happens when another core tries to interrupt? Suppose the same process starts normally. Core exclusive loads some memory, and then another core writes to the same memory. The other cache tries to invalidate the cache line in our private cache. And unlike in Intel processors, the request is not blocked. This cache line is indeed invalidated. And importantly, the exclusivity marker is reset. Now, when our core processes the value and wants to exclusive store it, it checks and sees that this cache line is no longer marked exclusive and the store fails. The hardware does not invoke a retry, and it is left to the software to loop until such an exclusive store succeeds. An ARM core does not stall for anyone. And this is the distinction between C++ atomic operations compare exchange weak and compare exchange strong. Compare exchange weak is a naked invocation of load exclusive, then exchange or increment, and then store exclusive, which can fail and return a failure to the software, and it would be up to the software to retry if it so chooses. Compare exchange strong is a library call that manages this retry loop for you. It's not really a library call, it's a compiler intrinsic, but it is still a call, almost certainly inlined. Two additional notes I want to make on these instructions in ARM. First, the LDXR STXR pair of instructions has an arguably more useful cousin, LDAXR and STLXR. These load acquire exclusive register and store release exclusive register. These two, in addition to the load store exclusive mechanism, also enforce acquire and release ordering, same as load acquire and store release. That is actually quite necessary when you want to implement higher level synchronization primitives like mutexes, which we won't get into here. And the last thing I want to say on this is, well, actually, it's a riddle that baffled me for a while. Why do we need the exclusive monitor? Why can't we have some special store flavor that just fails if the private cache line is in an invalidated state? This wasn't obvious to me at all initially, and I think I will leave it as a riddle in this talk. You're welcome to suggest your answers in the Discord channel, or we can discuss it later at the Gather Town. Okay, before wrapping up this talk, I have a confession to make. I need to acknowledge a small implicit lie that I repeated throughout this talk. So far, we met only two potential states of a cache line. It could be valid, or it could have been invalidated by a write to the same memory from some other cache. In reality, this is a gross simplification. The most basic level, a cache line can be in any of the four states: modified, exclusive, shared, or invalid. The cache controller maintains a state machine for each cache line, and these states, along with transitions caused by actions of the owner core and other cores, are called a cache coherency protocol. Invalidate is only one request that can cause such a state transition. The most basic protocol is called messy for obvious reasons, and it has a few developments. The most famous two are MESIF by Intel and MOESI by AMD. The extra O stands for the added state owned, and the extra F stands for the added state forwarding. Actually, forwarding is easy enough to explain here. When several caches hold the same memory in plain messy, they're all in state S. They're all in state shared. If a new core wants to acquire the same memory in its private cache, someone needs to forward that memory to it, and it's not obvious who is that someone. The extra state F marks the forwarder and saves the real-time decision every time such a forwarding is required. There are many other variations and improvements to messy that I won't get into. Suffice it to say, there's more to cache communication than invalidate, but I think you can get by with a fairly decent mental image of the processes that go on inside the processor without this extra detail. To sum up, a short map of what we went through. Different cores can have different views of memory because write buffers and invalidate queues and non-multi-copy atomicity and reorder buffers and speculative executions, and probably more. What software does about it is fences, read, modify, write atomic operations, and high-level synchronization primitives that are implemented on top of these two, that are very worthy of their own talk, but we won't get into here. So I imagine this is a lot to take in 1 hour, and I want to say two things about this. First, we are in a C++ conference, so chances are you're writing for servers, and as of March 26, the server market is still predominantly x86-64. So if that is your case, you can be content to walk away from this talk with a good mental model of just FIFO write buffers. I'm actually curious now. Can you please raise a virtual hand if you write to other architectures, not x64? I'm not sure I can see it here. Okay, maybe I'll ask again later and gather them. Second, I submit that even if you do not need to consider the various concurrency pitfalls in ARM or other architectures, and as complicated as the hardware design is, it is still simpler than the contract that the C++ standard advertises. And it is still beneficial to have at least a rough mental model of the hardware implementation. To understand what the standard has to say about ordering, you need to understand the distinction between happens before and strongly happens before and dependency ordered before and inter-thread happens before and etc., etc. I submit that it won't be easier. It is natural to think that the standard exposes some abstraction layer to protect us from having to understand the details underneath, but this is not the case here. The standard plays a different game. It exposes a phrasing that has to be very abstract to apply to all current and future implementations of compilers and hardware, and so it is forbidden from saying anything concrete. Simplicity is definitely not the motivation for C++ memory order specifications. To properly grok C++ memory orders, I really recommend to try and have some mental model of the hardware, even a rough one. Oh. That's all I had to say. Thank you very much for listening, and I'll be happy to answer and discuss anything in GatherTown or in the conference Discord. I'm going there right now.